Welcome back to Integral Calculus. In this video, I'm going to change gears and talk a little bit about sequences. Everything that we have dealt with in calculus has relied on an important structure of the real numbers. That is specifically the continuum. A real number has a nice property that if you look at any two real numbers on the number line, you will always be able to find a new real number somewhere between them. At least one, and in fact, because there are at least one, there have to be infinitely many. Because once you found that one, well then there must be one here, and there must be one there, there, and there. Right? The real numbers have this property, and in fact, even just the rational numbers, the fractional values, have this property. Compare that to the integers, right? For the integers, you can have 0, you have 1, you have 2, you have -1, and you have -2. If you try to pick something between, to get there, you have to leave the integers and go to a different set. So if we insist that we are going to stick with the integers, we don't have an in-between. The whole numbers, same story. Right. I'm going to use those terms interchangeably in this lesson. When we're working with sequences, we're almost always going to be working with sequences that are defined for positive integers or for non-negative integers. Every now and then we will work with something that's defined for all integers. One of the nice things about sequences is that it doesn't matter if there is some cutoff below which things don't work. Right? You can have something that's defined for an integer starting with 5, and everything will work fine. So I'm going to use the terminology interchangeably. We are going to be dealing with only the positive whole numbers, may or may not include 0. We're not going to worry about those sorts of details because they don't really affect anything. So we have had a real valued function of one real variable. And because that is an awful lot to say, we almost always condensed it down into notation, and we said that the function f maps from the real numbers to the real numbers. A sequence is a function. We're going to be a little bit general, and we're going to deal with real valued sequences. We could restrict this even further and insist on integer sequences, but it's not that interesting in the calculus sense. Anyone who has taken or plans to take in the future a course on discrete mathematics, the whole idea there is integer sequences of integer variables. Right. But for a sequence in any event, it is a function. We're going to call it a, but instead of mapping from the real numbers, it's going to go from the integers to the real numbers. Or depending on the needs, we might go to the natural numbers. As I said, I'm not going to quibble about the differences. The starting point of our sequence, the lowest value for which the sequence as a function is defined, isn't going to have any effect on the things that we want to do with the sequence in this course. If you move onward, that might become something that you need to worry about in other courses, but none of the tools that we're going to be looking at today are going to change whatsoever. Perhaps the most confusing thing about sequences is just the notation, because even though a sequence is a function, the fact that it's defined on a discrete set makes it feel different. And for that reason, instead of saying a of x or a of k or anything like that, we tend to use subscripts. So a subscript k is the function. And let's go with a relatively straightforward one, 2 to the k minus 1. We can evaluate this sequence the same way we evaluate any other function. Right? I can plug in 0. That gives me 2 to the 0 minus 1, which comes out as 0. I can plug in 1, which gives me 2 to the first minus 1. That's 2 minus 1, which is 1. A2 is going to come out as 3. A3 is going to come out as 7. And I'll list one more just for the sake of completeness. A4 is going to come out at 15. This particular sequence is important. The importance is of no value to our class, but it's a fun one, so I wanted to point it out. This is what's known as the Mersenne sequence. And the Mersenne sequence is notable because when your subscript is a prime number, like 2 or 3, the result tends to come out as a prime number. When your subscript is a composite number like 4, the result tends to come out as a composite number. And in fact, it's been proven that when the subscript is composite, the result has to be composite. When the subscript is prime, it doesn't have to be the case that the result is prime, but it often is. Right? But prime numbers are well beyond the scope of this course, so we're not going to worry about that any further. And instead, before I move onward, I am going to at least quickly mention the other notation. Right? Because the sequence tends to have this nice order, right? 0, 1, 2, 3, 4 as our inputs, there's no real other way of going about it. You'll often see sequences listed as an ordered set, which is a little bit confusing because sets are supposed to, by definition, not have an order. So this is not a set, this is a sequence. The notation looks the same. It is serving a completely different purpose. That's confusing. I'm not going to be using that notation in this course, but I needed to mention it because depending on where you're going after this course, that might be something that becomes important. That takes us to a common idea in sequences is a recursive sequence. Right? Our Mersenne sequence is very nicely defined. Given any index k, you have an explicit formula that you just evaluate in order to figure it out. But you don't have to do it that way. So for example, I could say that ak is 2 times ak minus 1. Although I do need to establish some sort of a starting point. So whenever you have a recursive sequence, you always need to have an initial point, maybe something like a1, let's make it a0 equals 1. Then from there, a1, if k is 1, then k minus 1 is 0. So we have a1 is 2 times a0, which is 2 times 1, which is 2. a2 would be 2 times a1, 2 times 2, which is 4. a3 would be 8, and so on. Both formats are completely valid for anything you want to do with calculus. I don't think it's going to be a surprise to you to learn that when you are given an explicit evaluation formula like this, it's a lot easier to work with, but a recursive sequence is also perfectly valid. Probably that sort of an idea is fairly familiar to you. Even if you've not technically worked with the vocabulary, sequences are a very natural aspect in mathematics. So I guess the interesting question now is, why am I bringing it up in calculus? All of the tools that we've worked with in calculus rely on the continuity of the real numbers, the continuum property. You can't get closer and closer to a value if there's no step in between. So derivatives are out. Integrals are out. Tests for continuity make no sense. But if you think about it, there is one thing that we can still do. In general, we can't take a limit. But if I specifically choose to take the limit as k goes to infinity of ak, that's something that will be defined. This formula should look very familiar to you. It is almost identical to the definition of the infinite limit for a real valued function. We say that the limit as k goes to infinity of ak is equal to L if and only if for every epsilon greater than 0 there exists an n in the natural numbers, so that whenever k is greater than or equal to n, the absolute value of ak minus L is less than epsilon. The only difference between this definition and the real numbers definition is that we have a sequence ak instead of a function f of x, and of course k goes to infinity instead of x goes to infinity. And we have our n has to be a natural number instead of a real number. Those are the only differences. Everything else is exactly what you expect. Notationally, in this course, I'm going to stick with writing out the limits longhand because that's what we do. But I do also want to mention that when you're dealing with sequences, you can write out ak goes to L. That is technically correct and is equivalent to saying that the limit as k goes to infinity of ak is equal to L. You might run across that at some point. If this limit exists, if we can find such an L, we say that the sequence ak converges to L, or we just say that ak converges, or we call ak a convergent sequence. If it doesn't exist, we say that the sequence diverges. We call it a divergent sequence. Nothing too crazy there. Hopefully that's vocabulary that makes sense. Just like with limits, we do our best to avoid using that definition because it's really messy, but there is a pretty straightforward example. If I think about the sequence ak equals 1 over k for k greater than or equal to 1, so again, right, where we start is going to not be important. I can't start at 0 here because 1 over 0 is undefined. And because I can't start at 0, I don't even want to think about negative numbers. But I'm really concerned about what's happening for very large numbers, so I don't worry about what's happening at the beginning. All right, so we'll have ak equals 1 over k. All right, pick an epsilon bigger than 0. Right? Relatively small epsilon is usually what we're looking for. Technically, to be correct mathematically, we should just leave it at that, but let's pick a particular one. How about something like 0.0001? That is 1/10,000th. And we want to pick an n that is bigger than 1 over epsilon. All right, so we take 1 divided by 1/10,000th, we get 10,000, and then we pick the next biggest integer. If this didn't work out to be a whole number, we would round up. In this particular case, I chose something that does work to be a whole number, so we just increase by 1. So n is going to be 10,001. All right, so if k is bigger than or equal to n, so we pick something bigger than 10,001, like maybe 25,000. Then the absolute value of ak minus 0, which is 1 over 25,000, or as a decimal, 0.00004. And the important thing is that that is less than epsilon. That is less than what we came up with over here. Pick any other value for k, that is still going to be the case. And so the thing that I plugged in as my L in this case was 0. The limit as k goes to infinity of 1 over k is equal to 0. Which should not be a surprise to you. That's kind of how, at least if you had me for Calc 1, that's how I defined infinity in the first place. But now we have circled around far enough that we can put that idea into a little bit of a more sure footing. There is no one official definition or one name for this process. I've seen a couple of textbooks that call it the limit comparison test. I've also seen a couple of textbooks that use a different thing and call that the limit comparison test instead, so it's confusing. Don't worry too much about the name. So let's take any sequence ak, and we're going to pick a function. I'm going to generally want this function to be continuous or in some way nice and easy to work with, so that f of k is equal to ak for all integers k. If the limit as x goes to infinity of f of x is equal to L, then it must be the case that the limit as k goes to infinity of ak is also equal to L. One of the important things about this theorem is the if-then statement. If you chose a function that has a limit and you set it up so that the function is equal to the sequence at all integers, then this works. If you did not choose a good function, you might have a case where a sequence has a limit that works and your function does not have a limit that exists. All right, so I'm going to start off with a terrible choice. Consider the sequence ak equals 0. I don't care what integer I'm looking at, I spit out 0. It is the most boring sequence I can possibly imagine. I think that you will be convinced, without having to do the work, that the limit as k goes to infinity of ak is going to be equal to 0. Now consider the function f of x equals sine of pi times x. In general, the sine wave is going to be an oscillating function. And because I have that factor of pi, the period here is going to be 2. So the x-intercepts of this function are going to occur at integer values, right? Sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, and so on. Since the pi is already there, this gives us the result. But that also means that f of k is equal to 0, which is in fact ak, for all integers, which means that these would match up. But this is completely useless to us because the limit as x goes to infinity of our function f of x does not exist. The function keeps oscillating between positive 1 and negative 1 and all of the real numbers in between. There is no bounding point, there is no asymptote, there's nothing that the function is tending towards. This is not useful to us for the theorem. Right. I guess the question then is, why even mention that? Well, I mention it because I wanted to stress at least a little bit as to how generalized this theorem is. Right? It does not give any indication of how you generate your continuous function. It just says, assume that you have one. In most cases, generating that function is fairly straightforward if you have a sequence that is explicitly defined, right? You have an evaluation formula for the sequence. If you have a recursive sequence, it's a lot harder to do that. But if we do have a sequence that is nicely defined, like ak equals k squared over 2 to the k power. In this case, much as we could have in the previous example, it's a fairly straightforward approach to just replace all of the k's with x's. F of x is x squared over 2 to the x. And now we have a continuous function to come off of that. When we have this situation, that sort of thing is easy. When we don't have the explicit evaluation formula, that's where things become harder. Of course, this isn't perfectly easy because if I try evaluating the limit as x goes to infinity here, I'm going to get the infinity over infinity indeterminate form. And I have a transcendental function 2 to the x in the denominator. So I'm going to try using L'Hopital's rule. That'll give me the limit as x goes to infinity of 2x over the derivative of a to the x is a to the x times the natural log of a. So we get an extra factor of natural log of 2 in the denominator. That doesn't help us because this is still going to be an infinity over infinity indeterminate form. It still has a transcendental function in its denominator, so I'm again going to try using L'Hopital's rule. Right, well, the derivative of 2x is 2. The derivative of 2x times natural log of x is 2 to the x natural log of x. I'm sorry, natural log of 2 times the natural log of 2 that was already there. Right? Natural log of 2 is a constant. We don't have to do anything with it. But the derivative of 2 to the x is going to introduce a new one. But at this point, we have the result comes out at 2 over infinity, and we know that that's going to go to 0. So our sequence here, ak, is also going to go to 0. All of the tools for dealing with limits on continuous functions are still valuable to us on dealing with these sorts of limits as well. Last thing with sequences is some vocabulary that should be very intuitive. A sequence is called bounded above if there is some real number m, so that every element in the sequence is smaller than m. A sequence is called bounded below if there's some little m, so that every element in the sequence is bigger than little m. It is possible to have a sequence that is both bounded above and bounded below. Right? A sequence that alternates between positive 1 and a negative 1 is a classic example there. A sequence is called monotonically increasing if every element ak plus 1 is bigger than the one that came before it, ak, and monotonically decreasing if the next element ak plus 1 is less than the one that came before it. You can get rid of the word monotonically and put the inequality to greater than or equal and less than or equal, but that's not always very useful. One of the places where sequences are different from functions, because there is no in-between, you don't have to worry, or you can explicitly avoid the case where the sequence stalls out and stays at the same place. And the reason that those definitions are useful to us is when they pair up. If you have an increasing sequence that is bounded above, it must have a limit. If you have a decreasing sequence that is bounded below, it must have a limit. That limit is called either the least upper bound or the greatest lower bound, depending on which way it's going. But that's one of those places that you have to be a little bit careful. Okay. For example, the sequence ak equals, let's say, 5 minus 3 over k squared. As you pick values of k, right, try picking k equals 1, you get 2. Try picking k equals 2, you get 5 minus 3/4, which is 4.25. try picking another value, right? K equals 3. Well, you get 5 minus a third, which is about 4.67, and so on. The thing that you are subtracting is getting smaller and smaller and smaller, which means that the value of the sequence is getting bigger and bigger and bigger. This sequence is bounded above, though. There is a point at which it can get no larger. Well, 25 is an upper bound. And so is 4,000. There are more. And so that's why the theorem here is not all that useful. If you have the least upper bound, the smallest number that serves as an upper bound, that is going to be the limit. Finding that least upper bound means finding the limit. So it's a circular argument. But at least we know that the limit does exist and it's not a wild goose chase. So with that in mind, I would like you to first list out the first 6 elements. I've listed out the first 3, so that's 3 more for you. And then once you have done that, find the limit using the limit comparison test that is basically the only thing we have right now. Right, take a couple of minutes, see what you can do with that. I'm going to figure out what's going on behind me, and I'll see you in the next video.